Okay, right. So let's begin this class today. Welcome to ECE 420, CMOS analog and mixed signal IC design. And today we will learn about the various configurations of the current mirror. We have seen various ways of current mirror and how do you improve the output impedance, how do you increase the gain using a cascode. So you've gone through all of that. Now you will see what happens after that. So next 40 minutes, we will try and cover some of the famous configurations that have come up. And why do we need that? Right? First need for various current mirror configuration is trying to understand what is it. First, what are the requirements for current mirror? Means for current mirror. The requirements for current mirror, first thing is, what is the output impedance? What is the output impedance present? And this you need to be as high as possible so that it can mimic an ideal current source. Second would be, what is the voltage headroom? Meaning how much voltage there is above for swinging. And this is extremely important for low voltage applications. Now, what would be the example? Let's take our simplest example. We have the reference current followed by the diode connection followed by the output current here, M1 and M2. And the expected output current is coming here, I out, and that reflected would be IREF. What are the other ones? Next is you have the geometry. W by L, what is the geometry available? Now for this, what is the current looking here? Current looking here would be R out is equal to parallel currents. What are the parallel resistance that are available? 1 over GM times R naught. By now you are familiar with the small signal analysis. So with multiple repetitions, you should be able to gather this. Now, what would be the voltage output that you see? The V output minimum would be the VDS sat. What is the VDS of this device? So that would be VDS sat. Lastly, what would you have? What is the ratio of the currents? I out over IREF. What would that be? The ratio of the VDSs, right? 1 plus lambda VDS2 over 1 plus lambda VDS1. So these are the two things. What else are we looking into? What else would be needed here? Right? Anybody? Okay. Now we will now look at configurations which help in improving output impedance and the voltage headroom. And the first of them is called a configuration wherein you do two things. One is replace the current reference such that the voltage headroom changes. How does that look? This is your reference current. Instead of having the diode connection here, you move the diode connection to the other side. Right? Once you have a diode connection, you add another device here. What you do? You add the device to this point, connect it here. Now, what does this become? What does this become? This is I ref. This is I out. Now, if you notice, this is a VGS. So you try and apply a VGS, PMOS VGS here to get the desired output. Now, what does that give you? What does that give you? Gives you two things. Let us recalculate the same three terms. What is the R out here? R out will be seen at this point. This R out is given as the ratio of the GMs of these devices. Okay, let me call them M1, M2, M3. So we know this is a cascode device. So what is the gain of the cascode? The ratio of these two GMs. That would be GM3 by GM2 multiplied by RO3, right? Now GM2 is supposed to be here times GM3 RO3, gain of this device. Then what is the gain of this resistor? Because this is reflective, right? This is a current mirror. So it will be GM1 times, if there is a load resistance, RL. Okay. What is RL? This is equivalent of generating the same factor. Right? If you have this resistance RL that is present here in place of the IRF, so that would be RL in parallel with RO1. See, now here you have one gain term here, another gain term here, times 1 over GM, GM2. What is that? That is the load seen here. Right? So this is a gain, this is a gain, this is multiplied the gain factor here. So if you see the gain of this device, GM2, multiplied by the gain of this device. Right? This gain term is this one, this gain term is this one, multiplied by 1 over GM2, which is the gain, resistance here of the impedance. So this would be the total resistance that you will see at the output. Now, what is the ratio of I out over IRF? I out over IRF is a function of VDS. So this is lambda VDS2 over 1 plus lambda VDS1. What will this become? Right? Now this would become 1 plus lambda VDS2. But there are two gain factors here, right? So now you have to take care of VDS2 plus this VGS3, right? Total. So it will be 1 plus lambda times VDS2 plus VGS3. It will not be VDS1 because it is now not dependent on this term. Okay. Then if you look at this gain value, this is higher than the regular current mirror. Right? Next, we will see what is the V out min, right? So let us see what is the V out min. The V out min will be given as what is the V out min? VDS3 plus VGS2 or DS2, either one you can call it. So it is VDS3 plus VGS2 since it is diode. Now that you should be greater than the VT plus 2 VD set. Sorry, 2 VT. It would be 1 VT of this device plus 2 VDSs of the stacked devices. 2 VD set. Now, what would this give rise to? If you compare to the previous one, just VD set, your V out min is lower. So you have a lower headroom. Headroom is smaller. Okay, here, so what do we have? Two factors here. One, R out has gone up. So V out min also has gone up. So headroom has come down. Okay, this configuration is called the Wilson current mirror. It's a very famous analog circuit designer, Wilson, proposed that I don't mind having a lower headroom, but let me get a higher current mirror impedance, right? Let me get a higher R out such that I will be closer to an ideal current reference. So that was that design's aim. Now someone came up with said, okay, I see some problem here. Let us modify that. So what can we modify? So the proposal to modify was take the same current mirror. We know that it has certain issues. Well, how can we reuse it? So their proposal was as follows. Okay, so now we have again coming here that we are seeing, and this is an inversion that is happening. Now let us do something here. So their proposal was, why do I leave this node hanging? Instead of leaving this node hanging, I will connect a, what will I do? I will connect an diode structure here also, right? I will have a diode structure here also. In this case, I have an IREF here, I have I route here. Now it gets better for me, right? What are the things that is going to get better? If you start from this point, your R out will start from here and go all the way there and land up here. We will show how that matters. So let us work on the R out. R out is equal to, first thing is, what is the gain of this? GM3 RO3 times 1 over GM2. Okay, resistor. Now multiplied by these two devices. Okay, what are these two? The RL and GM right now will form a negative feedback system with a current source forming here. So that would be RL times GM4 over 1 plus RL times GM4. Okay, this is the effective multiplied by the total resistance seen at this point. So what is the resistance here? The parallel combination of this circuit, RL plus 1 over GM4. Now this one will be in parallel with R1 of this device. Okay, so this would be the total resistance. Once this is done, now we will have again, what does the Vout mean? Vout mean, if you see, is identical to the previous one. So this has not undergone any change. So that would be VD sat 3 plus VGS2, right? VD sat 3 plus VGS2, that will be greater than VD plus 2 VD sat. This has not undergone any change, but the resistance has undergone some change. Now let us look at what is the current ratio that is going to, we are getting there here. So the current ratio is expected to be I out by I ref is again a ratio of or value of VDS, right? So 1 over lambda VDS2 to 1 over lambda 1 plus lambda VDS1. Now that will get close to be, let us try to understand what will happen. Now what is VDS1 here? This is VDS1. Now VDS1 is equal to VDS2. This is this one, VDS2 plus this VGS3, right? Then minus VGS4, it's total device here, minus VGS4. Or you could say, what do you happen if you take the at these 2 points? At this node, what is this VDS? This VDS is equal to VGS. This VDS is equal to VGS. So now you have the VDS of the device 3, VDS F2, device 1. If you do KVL here, KVL in this loop, you have two matching sets, a VDS on either side opposite and the VGS on opposite side. So the opposite VGS comes this side, you have VDS left. Now what does that mean? If you effectively subtract these two, you get a value which is VDS1 approximately equal to VDS2. Now if you put that approximation into this circuit, you see this will nearly be equal to 1. So this circuit becomes free from non-ideal effects, right? Non-ideal effect will become lambda, gamma, VDS, all these can lead to non-ideal effects. So approximately this would be the non-ideal effects. This was given the name improved, okay, Wilson current mirror. So the aim of this particular circuit was to make it free from non-ideal effects. So that was tried to see if you can get a dependence on the circuit parameters. And since they are all crossly available, KVL will equally match and they are symmetrical on both sides, things get better and understanding comes out well. Now, once these two were done, people went and said, okay, we have cascode mirror, right? And we also spoke about it. We know that, okay, if you have a current mirror, if you add a cascode, right? If you add one set of a cascode, you get higher gain, but lower headroom. That has been the case with the previous two circuits also. Now, as you keep increasing, the logic dictates that you can keep on increasing the value till your voltage headroom allows circuit operations. So this is your IREF. This will end up being an E0. So the common way of writing down circuit would be M1 M2. So these are all your cascode circuits which are written in blue. And these things would have two factors. One, the R out that is present here will be extremely large, but it will have the value which is similar to R out n times and GM n minus 1 times, right? So that would be the high. So it is an extremely high value. But as your gain value goes up, what you will lose out is you will lose out on the headroom. So you will have lower headroom. So this configuration is called a multiple cascode current mirror. Okay. Now this is definitely do not use for following circuit. One thing would be low voltage application. Okay. And since these are there, this is also not suitable for low noise application. So you will not use this particular configuration of the current mirror in these two, and it is not recommended. Low noise, you could also call it for low power also, right? So low noise or low power applications would be not suitable for this one. Now that we have learned all four, let us do a quick summary, right? Current mirror configurations. Let us do a summary to understand how easy it is to follow. First one is we will write what are the configurations. What is the configuration? What is the current ratio, right? What is the output swing or the V out min for that, and what is going to be the output impedance, right? So what's the first one? First one is a simple current mirror. So single mirror current mirror ratio is 1 over lambda VDS2 by 1 plus lambda VDS1. What is the output swing? VD sat, only the VDS device. Output impedance will be 1 over GM in parallel with R0. So 1 over GM of the diode in parallel with the R0 device. Second one is cascode. So what is it with cascode? Cascode will have VDS2 approximately to VDS1. So the ratio is 1. Output swing is 2 VD sat plus VT. And your cascode value is R square over GM. Third, triple cascode. Okay, triple cascode also ratio will be the same because you are maintaining the same. Here swing will reduce. Triple cascode means 3 VD sat will go plus VT, and then when you have R out, this becomes RO3. This is GM2 square. Next, fourth one, Wilson. Wilson current mirror. Wilson current mirror is also similar to the simple cascode. So that is 1 plus lambda VDS2 by 1 over 1 plus lambda VDS1. Output swing similar to cascode. 2 VD sat plus VT. But the gain is also similar to cascode because one stage is only cascoded. So this will be R0 square GM. Last one, we will do improved Wilson. Improved Wilson, again this ratio is 1. The it is similar to cascode, VD sat plus VT, and the gain is also similar. Rho naught square by Gm. Now, if you look at this, what do you learn from it? If you learn that you can get maximum swing with only simple cascode, right? Maximum swing, but you will get minimum swing with triple cascode. But wherever you see the max and min, you will say in the gain also, output impedance also being cross. When there is minimum output swing, you have maximum output impedance, and vice versa on this case. And you look at it wherever there is a cascode, right? Cascode, Wilson, improved Wilson, all three are cascode circuits. Their outputs are very similar. So if you understand, if you look at cascode, find out what is the value, you can add them. The only disadvantage or advantage of Wilson is it still has dependency on the non-ideal effects. So you have lambda. In the cascode and improved Wilson, you don't have that. So you can use that readily. Okay. Now we will understand with a few examples how can we design, and these are going to be crucial for your projects. So please pay good attention. First thing is, let us do an example. Okay, now the below figure has a source degenerated current source. Okay, so there is a source degenerated current source. What you need to do, you need to calculate the output resistance. Calculate the output resistance using the given bias current. Okay, using given bias current. So what are the values that are given? You have a model given here. So here are the model details. The model is mu n Cox is equal to 110 microampere per volt square. Lambda is equal to 0.04, and this is defined for L equal to 1 micrometer. Okay, or if you go 1/10 or twice the length, you will vary your value slightly. So it is 1 for L equal to 2 micrometer. That is per volt unit. Last one is 2πf. Remember, this is a clue. Whenever they give you 2πf, that means you need have an option to play with the VT of the device. And gamma, when they give, this definitely is there if there is a temperature dependence. So these are the clue. This is for VT. This is for VT plus temperature dependence. So you need to find out. Okay. Now, what is the circuit that we have? The circuit looks like this is a 100 kilo ohm. This is your V gate. This is your drain current. ID is equal to 10 microampere V out. Right. Now, what is the W by L ratio? W by L ratio given is as simple 2:1. Now, how do you begin? Pay close attention. First, step 1. You just have finished your exam, so you will remember very well. Step 1, find DC conditions. DC operation state. What is it? First one you know is ID is equal to 10 microampere. Now with that, what is this is, let us call it as a source. So ID travels here. What is Vs? Vs is equal to ID times 100k. That is 10 micro times 100k. That would clearly give us 1. This is 10 power 2 plus 3, 10 power 5. This is 10 power 1 plus minus 6, 10 power minus 5. Minus 5 plus 5 cancel each other. Left over is 1 volt. Now, what is the source bulk voltage? Right? If it's connected to ground, then it is Vs. Right? So that is what it is. So if you just connect this to ground, then V source to bulk will be Vs. If this comes means you have a GMB factor. You should not forget that. Right? Along with that, you will also have, since lambda is there, you have the R naught factor also coming into place. So you can predictively know these are the things. Now let us quickly draw the small signal step 2. Draw a small signal diagram. Right? How do you draw the small signal diagram? First, Vs source 100 kilo ohm. So Vs. What is Vg? Vg is present. So this is your Vg. This is V1. Okay. Vs. So what is V1? Vg minus Vs. Then you have Gm V1 and correct Gm V1. And there will be GMB. GMB VSB. Now this is GM VGS. We'll keep it. Finally, you will have your R naught. This will be total ID, and this is the V out value at which you are testing. So now that you have drawn the small signal diagram, what is the output resistance? Output resistance is total R out. Now where is V out? V out is taken with respect to the ground. Plus minus. Easier way of doing it. What are the simplifications you can do? Quickly. People have now become experts in that. First one is KVL. How much is KVL? V1 is equal to Vg minus Vs. And Vs is given as ID times 100k, or it is 1 volt. Now what is left over? Find out Vd out minus I out. Easiest way of doing that, put a test voltage. This is Ix, this is Vx, test voltage. So your R out is given as a ratio of Vx over Ix. In this case, your Vg will be grounded, and so only you are left out with Vs over here. Correct? To find out what is the current flowing through these values. How do you look at it? So either you can find out what is the voltage drop across this R out, right? Or find out what is the current flowing through here. So easiest way of getting an intuitive answer is these two are in parallel. So it is VSB and those both are VS itself. This is VGS, VG minus VS. Here VS is ground. So it is minus VS. This is plus VS. So GM plus GMB. Okay. GM plus GMB is the VS current, right? I into R naught. Right? GM VGS R naught. Now this whole, if you divide by, multiply by R, that is this R, capital R, you will find out. Along with that, you have the two R devices, output resistance, right? This R plus this R. Okay. How does this typically look? Since you have multiplied by R, you get this factor. Otherwise, this would typically look as 1 by R out by R plus GMB gives GM R out. So this would be a total R out value that you have to get. Or if you can approximate this simply as the cascode device, right? This value into the gain of this value, you will get GM and R out of this device. GM R out of this multiplied by the capital R. That would be the total value, because GM and GMB approximately GM is larger. GM into R out into R. That would be your output resistance. Any doubts on this one? Now that you have got this value, you need to now perform the computation. Why? Because you have been given the model file. So what is the computation that needs to be performed? First thing is you need to find out GM, R out, and capital R. You need to find GM, R out, and capital R. Right? Capital R is known, it is given. R out is 1 over lambda ID. GM is, let's find out. GM, either you can do 2ID by VGS minus VT, or since we have been provided with a mu x number, you will get 2 times mu and Cox times W over L times ID, all the known parameters. So these known parameters will end up time being 2 times mu and Cox is 110 micro, 110 micro, W by L 2:1, ID 10 micro. So micro and micro within the square, you get micro outside. 2 and 2 to the square, you get 2 micron. What is left over is root 110, root 110. So how do you compute root 110 with 2 times 55? 55 will be given as 5 times 11 times 2. Now you do not have a number which is equivalent. So we need to find out what is root 110. I will try and bring up the calculator. 110. Square root of 110 is about 10.49. So 2 micro times 10.49 approximately. And that will give me, if you approximate this as 10.5 times 2 is 21, approximately 21 microsiemens. This is right. Have I made a mistake anywhere? Sorry, this is not, yeah. That is correct, right? Did I make any mistake there? 2 times mu and Cox, 110 micro, then W over L 2:1. Then ID is 10 micro. That is correct. Good. Next is we have after GM, we will find out GMBS. GMBS is given by GM times gamma over 2 times 2πf modular plus VSB, and the whole thing under root, right? So that approximately gives us the GM value. How much is 21 micro times gamma. How much is gamma? 0.4. Gamma is 0.4. Then 2πf is 0.7 divided by 2 times 0.7 times VSB. VSB is Vs. Vs is 1 volt. Whole square root. So that would be 21 micro into 0.2 divided by square root of 1.7. So that value is given as clear 1.7. Square root of 1.7 is 1.303. So 21 micro into 0.2 divided by 1.303. That value is given as 21 into 0.2 into 1.303. As 5.47. 5.47 micro. Okay. So now that we have these two values, we will find out what is R naught. Just a moment, I'll be back. Thank you. So last one will be what is R naught? R naught is 1 over lambda ID. So what is lambda ID? For L equal to 1 micron, 0.004. That would be 0.04 times ID, 10 microampere. What will that be? 1 over 0.4 micro. How much is 1 over 0.4? 4 goes 2.5 times, right? 2.5 micro becomes mega. Now, time to find out what is the final value. So the approximated value, instead of doing all this calculation, we will do is GM R out capital R. That value is given as GM is 21 micro times R out is 2.5 mega times R. R is 100K. 100 kilo. Micro cancel with mega. So you have 21 times 2.5. 21 times 0.5. 52.5. 52.5 times 100K, which will equate to be 5.25 mega, right? So that would be the approximately the max R out. So the mega ohm. Your R out is 5.25 mega ohm. Okay. Now, in the same circuit, right? In the same circuit, let us find out what is the minimum voltage as an extension, right? We found what is R out. Let us find out what is V out min. So how do you find out V out min? The V out min is given as what is a drop across this value and the VD set, right? And VGS minus VT. VD set would give you that. So first, let us find out the numerical. Numerical, what do you have? We need to find VGS minus VT. So this is what we have to find out. So in this circuit, what do we have? VS is equal to 1 volt and V out we don't know. So VGS minus VT from the current equation, you will get 2ID divided by mu Cox W by L whole square root. This is given as 2 into 10 micro divided by mu Cox 110 micro W by L 2:1 whole under square root. Micro cancels with here, 10 cancels with 10, 2 cancels with 2. So you have 1 over 11 is the square root. And that value is given as 11, 1 over 11 square root 0.301. 0.301 volt. So this is a VGS minus VT. VGS minus VT is equal to 0.301 volt. Now, with this, what do you get the VD min? To help you make it easier, what would be your VD min? Okay, VD min is whatever said and done. Minimum is this much. Then your VD set, VGS minus VT. So that value would be summation of these two values. So VD min is equal to PS plus VGS minus VT. That would be 1 plus 0.301, 1.301 volt. That would be the minimum VD min for this circuit. Now, if we do one thing is, if we replace, right, this particular circuit, we can replace with two active devices. One active device could be a diode circuit. Either you replace with a diode circuit or you can replace with a current source. Both will give you high impedance circuits. So if you replace this 1 over 10 with this one, what do you get? This 100 should provide the same value. So let us suppose you use this circuit. So the output impedance of the diode circuit is 1 over GM. In that case, 1 over GM should provide a 100 kilo ohm resistance. Okay, that would be the R out 1 of this device. So in that case, what would be GM of this circuit? This GM will be 1 over 100K or 10 over 1 mega. That would be 10 microampere per volt square. GM is present. Now, once you have this value, you know what is the current that is need to flow. So what is the current through this? Right? Current is 10 microampere. For 10 microampere, what is this? W by L ratio. We will call it M2. What is the W by L ratio? 10 microampere is there. Now you will use GM. Equation for GM. GM is 2ID, or you can say 2 mu n Cox W over L ID whole square root. What does this become? GM is known, mu n Cox is known, ID is known. You only need to find W over L. So W over L is given as GM square multiplied by 2 mu n Cox ID. So what is the GM square given as? 10 micro whole square by 2 into 110 micro times ID is 10 micro. So this micro gets cancelled with these two. This 10 gets cancelled here, so this goes away. So what is left over? 1 over 22. That means you have a W over L is 1 over 22. Now what does this mean? Extremely long channel L, right? So extremely long channel means high R out. Correct? See, you needed 100K R out. So you have an extremely long channel and narrow device. So you need to ensure that this extremely long channel can be supported in this case, so that you get value. This is all assuming you don't consider the W by L. Now in this case, we will call this as example 2. Now for the same condition, let us find out what is the V out mean. Now in this case, what will be the V out mean? Here V out mean is your VGS value, and this is again VGS minus VT. So what is the value that you have here? So V out mean will be VGS2, this is VGM1, plus VGS1 minus VT. So the previous calculation, we know this is 0.301. And what is the VGS value here? VGS value is VT value. How much is VT? What is the best way to find out what is VT? So from the current equation, so ID equal to mu n Cox W over L VGS minus VT. Okay. Now we only need to know VGS2 value. So for 2VD divided by mu n Cox W over L plus VT is going to be your VGS value. So VGS2 is equal to 2ID over mu n Cox W over L whole under root plus VT. So can we calculate this value? We can calculate this value as back value. You know what is VT? VT value is given anywhere. VT value is not given, so you need to find out VT somehow. What is 2ID? Mu n Cox W over L. So this is 2 into 10 micro over 110 micro times 2. then make plus Vt. So this is given as 1 over 11 plus Vt. So 1 over 11 is given as, this is 0.301 was 1 over 11, 0.301. Correct? How much is that value? I only need to know Vt. Now assuming let Vt is equal to 1 volt, then this value will be 1.301 volt. And what is the VGS value here? 1.301. So the total value will be 2.6 volt is the Vmin that you will see. Okay. How do we now? Before we close this session, I need to introduce you to variations. What are the variations in current mirror? It's an important topic before we close. Variations in current mirror. Now, what are all the possible variations we can do? Let us first draw the current mirror. Let me draw it neatly. This is the simple current mirror. IREF. Now, what all can get varied? Let's do the current equation first. ID is equal to mu n C ox W over L VGS minus VT whole square times 1 plus lambda VTS. So this is your typical current equation. So what are all can vary here? Important points. First thing is your process can vary. Mu n C ox. Then your geometry. W can vary. L can vary. Right? Then along with your process comes VT. So VT of your device can vary. So mu n and C ox are your process content. Then because of the process and your channel length modulation will also vary. So you have at least 5 varying parameters. And in the case, if you take an example, each of these 5 varies by plus minus 5%. Each of the above 5 parameters vary by plus minus 5%. Okay, what does it happen? So how do you vary? You will try and find out what is ID. So find out what is ID min and ID max, right? What is the range of the ID which this needs to get satisfied? So ID will now have a range. ID min and ID max with respect to these 5 parameters. So how do you begin? Let us start off with giving a fixed value. Let's say the W by L ratio for both of these is 3:1. This is your VGS. This is the VDS, right? And we will name the transistors as usual as M1 and M2. So what are the changes that you observe? So first one, when you have mu and Cox that you can vary, each one will have a min and a max. So what all will be min and max? Right? I out min, put a table here, I0 max. So if your current needs to be in, we will find out the various terms. So for each of the circuits you have K. K is defined as mu n Cox W over L. Okay, so that would be K1 and K2. Okay, once you have K1 and K2, next you will have W by L variations, right? So W over L1, W over L2. Okay, another set of variations. Final set of variation is your VT. So VT1, VT2. So we need to find what are the min and the max. So let us find out what goes where. So for I out, for I0 min, K1 is mu and Cox. If we need to be min, this needs to be max, the other needs to be min, right? So if you associate K2 here, this will become minimum, this will become maximum. Likewise, in the opposite side, when K2 is maximum, K1 will become minimal. Next, W by L ratios. If W2 varies more, then WL will become min. Now, when will W2 become more? When W2 has max condition, W2 will be more. So this will be max, this will be min. And when this is min, the max condition that will go is here. This will be min. Now again with VT, VGS minus VT. Which one will have VGS minus VT max? So when I0 is min, V2 will be max. Likewise, you will swap here. Then VT is min, I out will be max. So this is the variation that you will see across. Now you will have to find out, add the value. K1 plus 5%, K2 is minus 5%, W by L plus 5, minus 5, VT plus 5, VT minus 5. Keep all of these and then you will find the range. So this is how you have to aggregate over a period of time. Okay, so let us quickly summarize for today. One, what did we learn? We read about current mirrors. What are the various configurations of current mirrors? Configuration of current mirrors. What did we check here? We checked what is the R out. We checked what is the V out min, that is the swing that will get affected. Finally, we checked what is the I out by I ref ratio. How does that get impacted? Then we created a summary table. Summary table of all current mirrors. Current mirror configurations. Finally, we did examples to find out what is the, how do you find out I out and what are the corresponding values that you want to find with, what is it called? Your current mirrors. but your practical implementations. Replacing all resistors with transistors. So we found all of these, and finally we understood the importance of variation in current due to PVT changes, process voltage and temperature. So with this, we will stop today's class. Thank you for joining in the class.